In this video, we'll have a look at air and some of the basic gas laws that regulate the movement of air in and out of our lungs and also between the alveoli and the blood. So let's start. And let's just start with the composition of air. It's very easy to fall in the trap of thinking that air is just this one sort of substance, but it's actually a composition of a number of gases put together. And the main gases would be nitrogen, oxygen, carbon dioxide, and water. But it's not equal, is that if we actually look at nitrogen, we can see nitrogen makes up just under 80%, about 78%, 79%. And here I've represented them with the pink dots. So you can see most of what we're breathing in is nitrogen. Now I want to point out that all of these values we're looking at, and on the next page, really is making reference to at sea level, because we have to standardize where we're going to take these measurements so we have a baseline that we can all agree upon. So most of air is nitrogen, but of course, under normal conditions, nitrogen is not a concern, because the two gases we're really concerned about would be oxygen and carbon dioxide. So oxygen makes up about 21%, and we can see it represented here with the sort of brownish dots here. So it's not as abundant. It's much less abundant than the nitrogen. But when I compare that to carbon dioxide, which is only at 0.04%, that is much less than the actual oxygen. And then we also have water vapor. And water vapor, depending on a few things such as temperature and humidity, is anywhere from basically 0 to about 4%. Now these are the major components of air. Are there other things? Yeah, there are. Ozone, methane, helium, neon, and argon. We're not going to get ourselves bogged down in those because we really want to focus in on the ones that really under normal conditions we're dealing with in terms of gas exchange. Let's start having a look at one of the gas laws. And this is Dalton's law. Now, what does it say? It says the total atmospheric pressure is the sum of the contributions of individual gases. Remember in the last slide, the individual gases are things like nitrogen, oxygen, CO2, some water vapor. So what Dalton's law is says, okay, well, if I measure the pressure of this thing we call air, can I figure out what the pressure is of each of these individual components? And you can do it, and it's fairly easy. And as he said, the atmospheric pressure is the sum of the contributions of the individual gases. Now, we're going to call these partial pressures. They're the separate contributions each gas makes in the mixture. Now, this is at sea level. And once again, let me spend a second on that. Why at sea level? Because if I go up a mountain, the ratio of these gases is going to change. Less oxygen, the higher I go up. Think of people that climb Mount Everest. Often they have to use supplemental oxygen because there is less oxygen at altitude. So to standardize it, we think about sea level. And at sea level, we have this measurement, which I call 1 atmosphere. That's what this stands for, atmosphere, the pressure. And it's 760 millimeters of mercury. Okay. Now you may be sitting there thinking, what does mercury have to do with this? I didn't see mercury on the last slide. This is just because of the device that they use to measure. And they basically use a device, which is, hear me crudely draw it, okay, is that I have a reservoir of mercury here, and that if pressure is applied, the mercury, and I have a scale along the side here, that mercury will basically move up the column X amount. And that basically is how I take the reading. Okay, so it's basically a barometer that I'm using for this. Now, that's how mercury gets in here, because the device that they use to measure it is basically a reservoir of mercury. Under pressure, it moves along a tube. Along the side of the tube is a basically a ruler, and the more pressure there is on the reservoir of mercury, the farther the mercury will move up the tube, and that's why you get these weird numbers like 760 millimeters of mercury. Okay? It's just, that's the way it is. That's what they use to measure, and this is what happens to be in that tube. So yes, no, we don't have mercury floating around the air, and we're not doing gas exchange with mercury. All right. Now let's put that aside. So 1 atmosphere is 760. So now I know that the sum of all the gases is 760. How can I figure out their partial pressure, how much they contribute? Well, it's easy. I know the percentage that they contribute, okay? So nitrogen makes up about, well, we can just call it 79%. So I just take the percentage that nitrogen represents in that gas, multiply that by the total amount of pressure that I measured at sea level, and that gives me a partial pressure of 597. Right. We can do the same thing with oxygen. Oxygen's about 21%. So I just have to figure out what is 21% of 760, and it gives me the partial pressure of oxygen. Can do the same thing with water. Let's say it's about 0.5%. It gives me the partial pressure. And look at CO2. It's 0.04%, and that is, its partial pressure is only 0.3. So let's take a second and let's just kind of highlight, the two gases that we're really concerned about. And that is O2, and let's zoom in, and CO2. Now looking at this, in terms of partial pressures, I can tell that they're very different in their partial pressure. That oxygen has, at least out here in the air that we breathe, a fairly high partial pressure, especially when you compare it to the partial pressure of CO2. Okay. Now, when I look at the composition of air, the composition of inspired and alveolar air is different. Now, why? So think about it. If here I have an alveoli, that's an alveoli, and I'm going to move gases in, I'm going to breathe in, and I'm going to have that high amount of O2, that very low amount of CO2 in the air I breathed in. But think about, as the air sits here during and between breaths, it's not like the actions of the alveoli stop. That air sitting in here is going to be giving up O2 to the blood. And same thing's going to happen, is CO2 is going to be moved in during and between breaths. So the air that is left in here, in the alveoli, won't have the same composition as the air that is outside your body. Because when I brought that air in, some of the air has sat there. It's a little bit of residual air sitting in there. It's lost O2, but it's gained CO2. So when I start to look at that, I'll start to notice that all those numbers that I looked at in terms of partial pressure in the outside world are now a bit different in the alveoli. And think about that. When I inhale, so when I go to inhale, I'm going to have some residual air in here that's much higher than in CO2 than the air outside the body, and much lower than O2. So I'm going to mix the old air, because I don't get rid of all the air between my breaths. Otherwise, my alveoli would collapse. There's always some residual air there. So I'm going to be mixing sort of the older air with the new air, which is high in oxygen, low in CO2, and mix it with the old air, which is higher in CO2 but lower in O2. Right. So the composition of inspired and alveolar air is different. Why? First of all, remember, part of your respiratory system is about adding moisture to the air on the way down. So your alveolar partial pressure, that's what this is, partial pressure of water, is more than 10 times higher than the inhaled air. So there's going to be more water there than we just looked at. The other issue is that the alveolar air mixes with the residual air. So oxygen gets diluted and the air is enriched with CO2. And of course, alveolar air exchanges O2 with CO2 in the blood, which we just talked about. So if I start to look at the partial pressure of O2 in alveolar air, it's about 65% of the air I breathe in. So you can see that between the air just outside my nose I'm about to breathe in and the air in my alveoli, when I breathe it and it all mixed together, I'm only at about 65%. Now the other thing too is that the partial pressure of CO2 is about 130 times larger than it was, let me move back here. Because remember, these values that we looked at in the first slide, these are the values that exist outside our body. Okay? So you can see once I get inside the body and I bring air in, that the partial pressure of O2 is down because I'm mixing some old residual air with new air. But the partial pressure of CO2 goes up quite significantly because outside the body it's quite low, but because I'm mixing with this stale residual air inside, which is heavy in CO2, the partial pressure goes up. Okay. Now, talk about this, the alveolar gas exchange. And of course, you know from previous courses that there's something called the respiratory membrane. And we've talked about it, or we will talk about the respiratory membrane. This is where O2 and CO2 get exchanged. Now, the air in the alveoli is in contact with a film of water covering the alveolar epithelium. I do need this thin water layer. Can't be too thin, can't be too thick. It has to be just right. For oxygen to get into the blood, it must dissolve in the water and pass through the respiratory membrane, separating the air from the bloodstream. Right? So that's oxygen going from inside the alveoli into the surrounding capillaries. For carbon dioxide, it has to pass the other way around. But on the way out, it has to pass through a water layer, the same water layer that's inside that alveoli. So it doesn't matter which gas you are, you have to be able to get yourself through that water layer, that really thin water layer just on the inside surface of the alveoli. Oxygen has to do it, and carbon dioxide has to do it, or else I will not get gas exchange. So let's take a few minutes and talk about, well, how do they get across? And let me start by just drawing an alveoli. So here's our alveoli. There's an alveoli right there. I have a blood vessel right down here. And I'm going to make it green. I'm going to make a green water layer. And I have this green water layer just on the inside. And as I said, if you're O2, I want to get into the blood, I have to cross through that green water layer on the way in, plus other tissues. And CO2 on the way out has to also pass through that water layer. So let's talk a bit about this water layer and some of the things that really are involved with gases getting across. And that brings us to the concept of Henry's law. Now, first of all, I want to point out gases diffuse down their own gradients until the partial pressure is equal on both sides. Okay? Remember, the thing that really drives things is things go from high pressure to low pressure. Same thing happens here. Let's look at Henry's law. And at Henry's law, it says, at the air-water interface. Do I have an air-water interface? I sure do. There's that thin little water layer. And this is air out here, so that is an air-water interface right there. So, yep, I got an air-water interface. At an air-water interface, for a given temperature, the amount of gas that dissolves in water is determined by, you ready? Two things. Its solubility in water, okay, and its partial pressure. Now, it's not an either or thing. It's not like one gas would use just partial pressure and never worry about solubility, or vice versa, where a gas goes, oh, I'm just all about solubility, I don't care about partial pressure. Every gas has some combination, but every gas has sort of its main way of going, that it's not really a 50-50 split. So, these are the two things that are going to push CO2 and water across. Now, let's talk more about Henry's law. At an alveoli, the blood is said to unload CO2 and load oxygen. Okay, so that's moving stuff from the blood into the other tissue or into the alveolar space. And of course, the unloading of CO2 and O2 involves erythrocytes. Depends on how long a red blood cell stays in the alveolar capillaries. This is one thing to also consider, going back here, that a red blood cell doesn't just kind of travel to the alveoli and then stop. Kind of like a transport truck who backs into a bay to get loaded with stuff for 5 hours and drives away. This red blood cell is going to keep moving along. So we have to have systems that are pretty fast to allow gas exchange as this red blood cell moseys on by. And it's not a great amount of time. So now, gases will only move from the alveoli to the blood or the blood to the alveoli as long as there's a pressure difference in its partial pressure in the blood and in the alveolar air. Now, the nice thing is that under normal conditions, it only takes about a quarter of a second to reach equilibrium. So let me go back here. Let's say this red blood cell is coming by, and this red blood cell wants to drop off CO2. Well, it only needs about a quarter of a second in this area to drop off CO2. Because, of course, as it's moving, so it has CO2 in the blood. As it's moving by, CO2 is moving into the alveoli. And, of course, what's driving it? It's going from a high pressure or partial pressure to a lower partial pressure. But as soon as these two pressures become equalized, it slows down the transport. So when a red blood cell first comes in here, the partial pressure difference is going to be much greater. As I'm dropping off CO2, CO2 is going to start to build up. As I move further along, well, I have less CO2 to move, so the partial pressure is going to be a bit lower along here, but I start to gain over that quarter of a second more CO2. So during this journey here, it's going to drop off CO2, but as it does, the partial pressure here will increase in CO2, and the partial pressure in the blood will drop. And eventually, if they become equal to each other or close to equal, this reaction slows down. But that's okay, because all of this can happen in the time it takes for a red blood cell to go by. So, as I said, it takes about a quarter second to reach equilibrium. Now, at rest, the blood isn't moving that fast. It's moving, but it may have 3/4 of a second. So I only need 1/4 of a second. So that's 3 times the amount of time I need. So certainly even at rest, there's lots of time to reach equilibrium and get rid of some of the CO2. And conversely, pick up some of the O2. Now, how about at strenuous exercise, where the flow is faster? Well, even at strenuous exercise, it's about 1/3 of a second, and that's still more time than the 0.25. So it's still adequate, even at strenuous exercise. I still have enough time that as that red blood cell comes by, I can still do gas exchange. Now, the other thing to point out is that O2 and CO2 behave independently of each other. So they don't necessarily sort of look over their shoulder and go, oh, what's CO2 doing? Oh my goodness, I'll speed up, I'll slow down. They act independently, at least at the respiratory membrane. So one gas does not influence the diffusion of the other. Now it can influence the loading onto red blood cells or the unloading. And if you have not watched it, go watch the video I posted on systemic gas exchange. Now, here, what's the pressure gradient of the gases? Normally, if I'm looking at O2, it's about 104 in the alveolar air versus 40 in the blood. So you can see as that blood's coming by the alveoli that there's much more air. It has a higher pressure, partial pressure, in the alveolar space versus the blood. So that means that I'm going to get a movement of air, or air I should say, oxygen, I should be saying, into the blood. Okay. Now the same thing is that when CO2 in the blood arrives at the alveoli, it's got a partial pressure of 46. And in the alveoli, the partial pressure is 40. So there still is a difference. It's not as big of a difference, but that's okay. There's still a difference for an exchange to occur. We're not going to spend much time on hyperbaric oxygen therapy. Basically what they do is they use a larger gradient to hopefully get more oxygen into the blood. And just a reminder, at higher altitudes, the partial pressures of all gases are lower, so less oxygen diffuses into the blood. Okay, we're going to ease out there, and I just wanted to introduce a little bit about what 1 atmosphere is, how you determine partial pressures, and talk a bit about the gases at the respiratory membrane.